In this video, I'm going to show you really the only new design technique we're going to need for the Sudoku solver. It's a technique called template blending. Now once we have this, a whole lot's going to happen in this video, and it's going to happen fast. Because what we're going to see is we're going to take the idea from the last video where we saw that there were three things going on in the Sudoku solver. There was generative recursion, an arbitrary arity tree, and backtracking search. And we're going to take those three templates and combine them together. Things are going to go pretty quick. Now as we do this, we're going to step back a little bit from the way we've talked about templates before. We're going to relax them a little bit. But the fundamental idea underlying templates isn't going to change at all. Because what templates have always been from day one is they were the answer to a very simple question, which is, given what I know about what this function consumes and what it produces and basically what it does, how much do I know about the form of the function before I start on the details? Templates have always been that. They've been the outline or the backbone or the sketch of the function. And they're going to be that here too. But in order to put three of them together, we have to relax just a little bit to make that work. Here we go. Now I'm in Sudoku Starter. You've seen this before. You've seen all the data definitions. If that was perhaps a little while ago, I encourage you to pause this video and just take a quick look over the data definitions in the starter. But here we go. I'm going to go down to functions, and we want to design a function here to take a given Sudoku board and either solve it or say that it can't be solved. It's a backtracking search function. So the signature is that it's going to consume a board. Now remember what the method does. Oh, this solving a Sudoku board seems big and hard. But by focusing on the first step of the HTTF recipe, I know what to type right now. I need the signature of the function that does it. And it consumes a board, and it produces either a board if it finds a solution, or false if it fails. That's the standard signature of a backtracking function. And we say that it produces a solution for board, or false if board is unsolvable. And we're going to add one more thing, because the Sudoku problems that you get in the paper always start out at least being reasonable. They always have no contradictions in them. So we'll say that the board we start with is valid. It has no invalid entries in it. All right, well, let's do a stub, solve boards, and we'll just say false because it's the easiest thing to say. And now let's do some check expects. Well, there's not a simple base case here unless maybe we give an already solved board as a base case. Here it's a little bit tougher to sort of think about what to do first, but I've got some example boards above, so I'm just going to use them. Check expect solve board 4. Well, the solution for board 4 is board 4 solution. And the solution for board 5 is board 5 solution. And board 7 is unsolvable. So there's some check expects. Now let's template. Now what's going on here? Remember what we learned in the last video. We're going to generate an arbitrary arity tree, and as we generate it, we're going to do a backtracking search over it. There's three things involved. So the answer to the question, hey, what do I know about the basic shape of this function before I get down to the details, is I know three things. I know that it's going to include elements of the template for generative recursion, elements of the template for an arbitrary arity tree, and elements of the template for backtracking search. Let me start with an arbitrary arity tree. In an arbitrary arity tree, you've got nodes in the tree and then lists of nodes, because there's nodes and their children. So that's going to be two mutually recursive functions. I'm going to wrap them in a local. So local, there'll be two functions in here, and then there'll be a trampoline that calls the first function. So let's template the first function. This is going to be the function that operates on a single board. So let's see, we'll call it solve -- board. It operates on a single board. Now look, I'm working a bit from memory here. I don't have type comments for an arbitrary arity tree. Okay? But I'm remembering that the way an arbitrary arity tree works is its node, in this case board, and list of board. So I'm templating that from memory. So now what happens here? Well, what happens here is it's something like ... and then I'm going to do something with the subs of the board. Okay? So that'll be solve -- list of board of board subs of board. Now that little selector I've pretended to call there board subs doesn't really exist. I know that. Just hang on. And then the other function is going to be something like, I'm templating still, solve -- list of board, cond. Well, the list is either empty, in which case ... or it's not empty, in which case what? Well, it's just the usual template for operating on a list of x, ... first LOBD, except that's a board, and then rest LOBD, except that's a list of board. So this first of LOBD is the reference rule. That's going to make me call back to solve -- board. And rest LOBD is list of boards, so that's a self-reference. Solve -- LOBD. And I didn't quite name this function right. Let me just get my parens first. And this should be -- LOBD. I need the trampoline to start the whole thing out. We originally call it with a board, so the trampoline is going to say solve -- board of the board. So again, that's templated according to the arbitrary arity tree, but that's not the only thing that's going on. There's also generative recursion going on. And where the generative recursion comes in is there is no structure selector for going from a board to its children. Those have to be generated. So just to accentuate in my mind the fact that these are generated rather than a structure selector, I'm going to use a different name for this. I'm going to call it next boards. To me, that reminds me of the fact that I'm using the generative recursion template. And the generative recursion template also involves something else. This is where it generates the next boards. But if I go over to the generative recursion recipe page, you'll see that I've got to do something else here. And here's the next problem. That's why I named that function next boards. But I've got to test, am I done? I've got to do the trivial test. So that's what this if is, and this is going to be the trivial test. And jumping back again, if the trivial test is true, I do the trivial answer. But just as I picked a better name for next boards, let me pick better names for these two. What is the trivial test? How do I know I'm done? Well, remember, we're only putting valid boards in the tree, right? Because we talked about we're going to throw out the invalid boards. So we're done if we ever get to a board that's full, because every board we leave in the tree is valid. So if it's full, it's actually a solution. So this really is a predicate like it could be called solved, or it could be called full. Okay? I'll call it solved. Somehow that's a better name. If a board is solved, then what do? Well, then the trivial answer is even more trivial than this. The trivial answer is just to produce the board. I'm still templating, but I'm doing a little bit more than templating because I simplified that call to trivial answer and I picked a better name for solved. So I'm a little bit more than templating. So now look at what I've got. I've got arbitrary arity tree traversal. Here I'm kind of underlining that part in blue. And I've also got the generative recursion template. I'm underlining that in red. I still have to do the backtracking search. Well, what do we have to do for the backtracking search part of it? Well, I'll jump back over to the design recipes page. And let's see, I'll go to design recipes and I'll go to backtracking search. And let's see, this second version of it is the one we use when we've got local. And basically what backtracking means is that when we fail, we produce false. And we first try the first child. And if the first child succeeds, we produce that. Otherwise, we try the next child. So I'll go put that behavior into the template we've been building up. If we run out of choices, we're going to produce false. Otherwise, what are we going to do? Well, this thing here, I'll pick that up. We're going to say local define try that thing. So that means go try the first child. And if that's not false, produce it. Otherwise, try the next child. And I have to add one more paren here. So there we go. What I've done is to take the idea that the way we're going to solve Sudoku is to generate an arbitrary arity tree by, for each board, finding the valid next boards and throwing out immediately the invalid ones. And we'll just do a backtracking search over that tree as we go. And if we ever come to a full board, a board that is solved, we're done. And every time we fail, every time we run out of choices, we produce false. That's the core of the Sudoku solver. And the key thing that I did here, the one thing that we've never quite done before, but we've been building up to, is I relaxed the notion of template just a little bit to really what it's always been all along, which is the template is the answer to the question, what do I know about the core of this function before I get to the details? And in this case, that took me almost all the way. Now, we're not quite done here. I did wish for two things. I wished for this function solved ? Which was what the generative recursion template called trivial ? And I wished for next boards, which was what the generative recursion template called next problem. So this really is just the template. I just gave things a slightly better name, and I'm going to need wish list entries for these. And we're going to do that in the next video.